Ladies and gentlemen, thank you for joining the webinar Test Verification Setup today. Though we will be answering questions at the end of the presentation during Q&A, you can enter your questions throughout the presentation. Please submit them via the questions box in the GoToWebinar panel on the right side of your screen. It is now my pleasure to introduce our first speaker to you today. Mr. Massimo Ravazzini is the Regional Sales Manager for Measurement at Meggitt and Devco. Massimo?
Hello and thank you for joining us. My name is Massimo Ravazzini. Welcome to the Meggitt and Devco webinar, Test Setup Verification. In this webinar, we will discuss best practices to verify a test setup incorporating accelerometer, pressure transducers, electronics, and cables. This may be defined as a simplified measurement chain. Before we begin with the presentation, I would like to ask you a question to the audience now. Do you verify your setup before beginning tests or considering an installation complete? Vote now. Options given are always, it depends, and never. If you answered it depends, feel free to use the questions functionality to tell us what factors help you decide whether or not to undertake verification procedures. Validating the signal path from the transducers to the data acquisition system can try the patience of any test engineer. But every testing professional has a varied suite of validation methods, some even rather unique, to verify a transducer's location and functionality along the entire measurement chain. A thorough and exhaustive review of any of these methods could anyway consume more than the time allowed for this webinar. So, we intend to briefly illustrate several and indicate for which transducers and scenarios they are appropriate. A PDF of this presentation will be offered after the conclusion of the webinar, including contact information of our expert to allow for more in-depth conversations about these practices. Now, I would like to introduce my co-presenter, Mr. David Copley, as he's also at Meggitt and Devco as a Regional Sales Manager for UK and Ireland. He has worked extensively in the field of pressure measurement, as well as in the development of experimental vibrational stress analysis techniques. Also joining us during the question and answer session is Krzysztof Sonicki, our European application engineer, with over 8 years of experience in test and measurement applications. After the test methodologies are presented, we will address your questions. You are welcome to submit them throughout the presentation by clicking on the Ask a Question button in the interface located on the left side of your screen. David, why don't you start us off?
Thank you very much, Massimo. Many tests require transducer setup verification to ensure the data is valid, accurate, and meets the scope of the test definition and objectives. Why? Well, such setup verification is needed to identify and correct potential problems before pressing the Go button on the test. If not, retesting might either be expensive or even not possible at all. A typical list of verifications may include detecting a miswired channel connection or incorrect channel assignment, verifying that the cable run to data acquisition system is continuous, location of the transducer and its polarity, and also the gain and scaling, filtering, sensitivity, and other aspects of attached signal conditioning. Verification of the entire measurement chain is necessary before running expensive tests, making it possible to correct any mistakes and create confidence in the transducer's performance.
At this point, I would like to take another quick poll from the audience. Sometimes the sheer number of channels makes it daunting to consider verifying each channel. However, is it often this test that would be the most expensive to repeat and make the best case for undertaking such a project? Please tell us the largest number of channels you have ever installed for a test or a permanent monitoring installation by selecting the appropriate range. Vote now, and we'll pause for a few moments to let everyone to participate. Options given are 1 to 10, 10 to 50, 50 to 200, and more than 200 channels.
Okay, thank you, Massimo. As you can see on the slide, a very simple validation test method is a 2G turnover test, which verifies the entire system and is accomplished by simply orientating a low-range accelerometer to measure the acceleration due to gravity. Take one reading and then turn it upside down by 180 degrees in the sensitive axis to take a second reading. This would be appropriate for low-range piezoresistive and variable capacitance accelerometers. The change by inversion creates a 2G difference between the two readings, as shown in the photos. This will validate that the transducer is connected, appropriate signal conditioning is being used, and the expected gain is set for the measurement. Massimo, what are your thoughts on this?
Well, David, some piezoresistive transducers cannot be tested at all by performing a 2G turnover test, simply because a transducer with low sensitivity would have a very little output. Also, this test method may require the transducer to be unmounted from the test structure, perform the 2G test, and then remounted to it. In some cases, this may be time-consuming. I would consider the tap test method now as a very common one. It is important to understand that tapping is not done by hitting the accelerometer. The tap test is accomplished by tapping the structure near it, near the transducer. This test method allows the transducer to be mounted in its measurement location. The tap will ensure connectivity of the transducer, signal conditioning, and data system involved in the test. This is a quick test method that checks the end-to-end of the measurement chain. What do you think about this, David?
Yes, I do agree that hitting the accelerometer itself can be destructive, but the tap test method close to the accelerometer is one of the most frequent tests performed, though it does often require 2 or more people, which can be labor intensive. It also does not validate the amplitude or gain settings because the tap itself is uncalibrated. And if there are multiple accelerometers near the tapping location, multiple measurements will register from the same tap point. Here, though, is a different test method that addresses some of these challenges. In this case, it is a visual test method for a mounted transducer's location. Channel illumination is a new validation method based on Meggitt's patent-pending channel light device that solves some of the problems of tap tests. It's designed to enable a single test technician the ability to verify the location of an individual accelerometer in a multi-channel vibration test, all without leaving the control room. This is performed by activating the channel light from within the data acquisition system. For example, as shown on the screen, we have a Dataphysics Quattro data acquisition system, which allows the test technician to electrically reverse bias the LED using software alone. The 6-inch integral cable device is compatible with either TEDS or non-TEDS transducers, including IEP accelerometers. The channel light is inserted between the accelerometer and the normal connection coax cable. It features both a male and female connector. An integral LED light identifies the transducer's location. The main benefit of the channel light is that it eliminates the need to disconnect cables or touch the transducer to verify its location and connectivity. Verification should therefore take seconds rather than minutes per channel. Dataphysics has updated their software in their Quattro unit to be compatible with the channel light. They were the first data acquisition system company to enable this channel illumination technology. Massimo, do you have any thoughts on this new test method?
Well, thanks for asking, David. This is an excellent test method that has been missing in test setup verification so far. Of course, not any single test method does everything. However, channel illumination is an easy method to determine the mounted location of an accelerometer. In most larger channel tests, all the same color wiring is used, which is a challenge to troubleshoot the transducer's locations. However, the test method does not validate the functionality of the accelerometer itself. But for connectivity and location method, this is an excellent way to verify these parameters. Let's talk about some other test methods that do check the validity of the transducer instead. For example, a zero measurement output or ZMO measurement. It provides a good health check for variable capacitive or piezoresistive transducers. This measurement requires the attached signal conditioner to have this ability. Simply measure the transducer's ZMO and compare it to the value of the transducer's datasheet or calibration certificate. Any transducers off of the tolerance should be considered for replacement. Depending on the signal conditioner being used, the methods may be different in setup. For example, the Megit Model 136 signal conditioner can be set up with the auto 0 turned off, and the ZMO can be measured at the output of the signal conditioner or by the data system. This tests connectivity and signal conditioning, of course. Do you have additional thoughts, David?
Well, yes, I might add that the ZMO is the unbalanced output from a transducer, and that this test method does not verify the transducer's location or filtering, and in any transducer with a bad ZMO will suggest a critical imbalance in the bridge resistance. A more thorough test of the bridge can be accomplished using the following test. Measuring input and output resistance is a great method to verify a healthy transducer. This requires the transducer's output connector to be available for measurement with an ohm meter. This resistance measurement should be made at the first available connection point closest to the transducer. The resulting values are compared to the transducer's datasheet or calibration certificate if available, and an out-of-tolerance measurement should be considered for replacement. This true health check will tell you if there is an open or cracked bridge, as well as any significant changes or drift from the transducer's original resistance. This is thus a very easy method to check the integrity of the transducer. Do you agree, Massimo?
Absolutely, David. This is a good test method and I recommend it often to test lab professionals. We do need to remember, it does not check the integrity of the signal conditioning, the data system setup, or any applied low-pass or high-pass filtering option. Although labor-intensive, this is something that should be performed at any piezo-resistive device before a critical test. We can also consider another test method by exciting the whole measurement chain instead, by using, for instance, a calibrated excitation source, such as a portable handheld shaker. This is the most accurate method for a complete end-to-end system verification. For example, a 1G shaker will excite an accelerometer to verify transducer sensitivity settings into the data system, as well as any other configuration applied in the data system itself. Megit's reference mate is the only handheld shaker with 3 different fixed frequencies available of 61.4, 100 or 159.2 Hz, depending on the type of integration method your system is set up for, to obtain a measurement unit of 1. It is important to set the shaker for the appropriate amplitude, either for a peak measurement or an RMS measurement. This will be determined by the meter or the data system being used. The accelerometer is mounted onto the shaker and excited to a known 1G value and a selected frequency. This directly verifies the accelerometer integrity and the system setup. You want a quick check of a calibration and all connection from transducers to DAC. Well, simply put a no vibration in, get an expected reading out, simple like that. Would you like to expand on this, David?
Yes, what I can add is this test method is sometimes impractical, since it does require the transducer to be removed from the test structure and mounted on the vibration source, which may not always be practical or accessible. However, it may be the best method to verify the complete system for an important non-repeatable test. Another good measurement system test is voltage signal simulation. This may be accomplished by injecting a known voltage with known frequency into the measurement chain. This signal path verification test is used to validate the entire cabling from the transducer all the way to the data acquisition system. Voltage simulation can be accomplished in a number of ways. It could be as simple as connecting a battery to the input leads of the cable, or by using a more complicated and thorough test method with the use of a function generator or handheld signal source. Such a function generator or handheld signal source allows for the use of a calibrated signal that can be varied in both amplitude and in frequency. This would result in a more thorough method that can be used, for example, to verify the amplifier gain scaling settings and also the filter roll-off values for each channel.
However, David, this does not check again the transducer itself, but is an excellent measurement chain verification method. This can be also done for IP devices, actually. Specialized handheld signal sources like Megit 4830B will simulate the sourcing of a constant current measurement setup while sensing a known voltage signal into the system. For isotron or IP transducers, signal insertion simulates this IP circuit. This is frequently done to ensure that there is enough constant current from the signal conditioning to transmit the higher frequencies of interest into the data recorder. This is also a way to ensure the expected gain and sensitivity enter into the data system as appropriate. Out-of-band frequencies, up to 20 kHz with a 4830B type device, can also be simulated to validate the low-pass filtering of the system. Again, from a calibrated device, the signals are simulated and can identify environmental noise induced into the measurement chain. In the example, an inappropriate gain setting in the system clipped the signal that was simulating the expected event. Once this was identified, the gain was adjusted appropriately to allow a clean signal to be measured.
We can perform a similar test procedure for charge simulation and insertion in place of piezoelectric accelerometers. Megit incorporates this functionality as well in the 4830B for both single-ended and differential piezoelectric accelerometers. This handheld unit simulates the output of a charge mode accelerometer. The output can be set in picocoulombs for complete channel setup. The signal is adjustable in both frequency and amplitude, making it a very dynamic test that can identify channel noise as well as verifying out-of-band frequencies to ensure appropriate filtering is enabled.
Yep, all of these simulation methods are great for system setup verification. Let's talk more about the transducer side of verification again. Considering shunt calibration, that can be performed as another verification test for a piezoresistive transducer's channel setup, gain setting, and as well a proper cable connection. Shunt calibration is a physical connection of a calibrated resistance value across one non-active Wheatstone bridge leg. Some transducers have also internal shunt resistors installed for quick testing. Shunt calibration is a simply and potentially accurate means of simulating action of a strain gauge. David, would you like to share some thoughts?
Well, yes, this can sometimes be a complex procedure since some transducers do not have fixed resistors built into them. Even some signal conditions do not allow for this test method. I think it's probably best to put this topic to one side and let the audience email us specific questions on this topic. One last verification method applies specifically to pressure transducers. Piezoresistive pressure transducers operate on a very similar principle to piezoresistive accelerometers, since they essentially use the same Wheatstone bridge type of configuration. So for absolute pressure transducers, one simple test method is to obtain the current barometric pressure if it's available and compare it to the sensor's reading coming from the data acquisition system. An absolute pressure transducer is referenced to a vacuum, so the output should be the current barometric pressure. Also, for both absolute and gauge pressure transducers, a simple functional test is to apply both positive and negative pressures to the sensing part of the unit. This can be achieved using a simple syringe as shown on the slide. Alternatively, it is possible to do this using simple tubing and using the suck or blow pressure created from your lungs. Massimo, do you have any thoughts?
I like this test method because it's so seemingly simple. The only challenge may be in some installation where a tube or a syringe cannot get to the transducer, or where the transducer may not be removed. So, well, we have covered several test methods throughout this presentation. Some are new and other methods are unique. You have probably noticed that none of the methods detect every link in the transducer measurement chain. Each method has pros and cons that make it best or completely wrong for validating a specific test setup. It's all about understanding the capabilities and constraints and match them to your measurement needs. In this presentation, we hope to give you a sampling and enough information to begin to decide which techniques and tools will best validate your test setup. David, Schistos, and my email addresses are provided so that you can contact us for more information. But we would like to begin a discussion now. At this time, we'll open up the floor to questions, beginning with some that were submitted during the presentation. You recall, if you have a question that you haven't yet submitted, it's not too late. Just click on an Ask a Question button. Mr. Suniski will now step into our conversation to take care of your inquiries.
Our first question comes from Julie. The question is, I like your reference mate handheld shaker, but I need more frequencies than 3.
Okay. Handheld shaker is made for a quick and reliable verification of measurement chains to prevent gross measurement errors, which are mostly related to cables or channel swap or wrong electronics setup. Handheld shaker can excite sensor at 3 different frequencies, and very clear relations between the acceleration, velocity, and displacement values expressed in imperial units at 64 Hz or metric units at 159 Hz allow for the quick verification not only the accelerometers but also velocimeters or the displacement sensors. In practice, during the measurement chain verification, only 1 out of 3 frequencies will be used. So the concept of having 3 different frequencies has no relations to the sweep sign calibration. If the verification at more than 3 frequencies is needed, Megit provides a portable calibrator, in case of which any frequency from 10 Hz up to 10 kHz can be set by user. Also, other standalone solutions like automated accelerometer calibration system are available.
Our next question comes from Paolo. I have a piezo-resistive accelerometer with 4 active gauges. Can I perform shunt calibration?
Accelerometers with all 4 active gauges cannot provide stable resistance reference. Therefore, in their case, shunt calibration is technically possible, but it will have a very low accuracy. Reliable shunt calibration is possible only in case of sensors featuring high-precision fixed resistors. These resistors provide fixed reference, thanks to which we know what imbalance of Wheatstone bridge is caused by the shunt resistor. The actual output of imbalanced accelerometer can be compared to expected value, so the measurement chain verification is possible. The one comment I would like to make is that the term of shunt calibration can be a bit misleading, because shunt calibration is not a true calibration. As I said, it is rather the measurement chain verification method, which cannot substitute a true calibration carried out on a high accuracy calibration system.
Our next question comes from Fanyani. The question is, what is the danger of using accelerometers with high ZMO after zeroing?
Uh, well, the danger is that some of the conditioning systems are balancing the ZTMO only within given range. So if we have the sensors with a large ZTMO, they may not be balanced. And this is, for example, the case of the absolute pressure sensors, which, when they are not subjected to any other pressure than atmospheric pressure, can give significant output, especially in cases of the sensors which measurement range is around 1, 2, 3 atmospheres. So 15 up to 50 psi. So the danger is that the conditioning system may not manage to balance them.
Our next question comes from Matthew. Does your channel light work directly with piezoelectric accelerometers?
LED channel light does not directly work with the piezoelectric accelerometers. To function, LED channel light requires IEPE power supply supporting TEDS feature. Why the TEDS feature of IEPE power supply is necessary? TEDS is accessed only when the polarity of the IEPE power supply is reversed. And internal accelerometer diode directs the IEPE power through the transducer memory, not the internal IEPE preamplifier. LED channel light features similar diode, so once the polarity of the power supply is reversed, small part of the current from IEPE power supply powers the blinking diode. Accelerometer to which LED channel light is connected does not have to feature TEDS, but the data acquisition system has to be able to support it.
And just a reminder, if you'd like to submit a question, please do so now. We have 2 questions currently in queue. Our next question comes from Marco, and he asks, can I perform shunt calibration for a VC accelerometer?
No, that is impossible. Shunt calibration cannot be applied in case of the variable capacitance accelerometers. In spite of the fact that both variable capacitance and piezoresistive accelerometers can be used with the same conditioning system supporting shunt calibration, the difference in internal construction are causing that the shunt calibration cannot be performed in case of the VC sensors.
And our last question from Matthias. According to the sensor output simulator 4830B specification, it can simulate single-ended voltage output. Can I use this single-ended voltage output to simulate differential voltage outputs?
Well, the differential voltage amplifiers may feature a different internal construction, so I cannot provide a general yes or no answer to this question. 4830B single-ended voltage output is simulating the signal in the way that voltage in one of 2 signal veins is dynamically changing. In the other vein, the signal is stable and close to 0. So as long the voltage output BNC shell is connected to the negative input of the differential voltage amplifier, and it remains isolated from the ground, and also the amplifier can cope with such an asymmetric signal, it is possible to carry out measurement chain verification. I know that this explanation this answer is quite complex, but in case of the ENDEFCO differential voltage amplifiers, there will be no problem.
That's all the questions that have been submitted. Massimo, I turn things back over to you.
Thank you very much, Don. Thank you then to everyone in our audience for attending our presentation, and thanks for your active participation with questions. We have just one more question for you, and it's which future webinar would you like to attend? Options given are at point A, single-handed versus differential accelerometers, at B, comparing accelerometer specifications, at C, extreme high temperature challenges, at D, minimizing the thermal effects. I give you some time to reply. All right, though. Thank you again for joining us today. You will receive soon the presentation and a link to the recording shortly. Have a good evening. Bye-bye.